Hi everyone, this is Lab 5 of Falling Slinky. The purpose of Lab 5 observes the motion of a spring system that stretches and then drops to the ground. This motion is modeled using computational models. The motions from this lab are based on physics principles, which is Newton's second law, also known as the momentum principle, which relates the net interaction between a system and its surroundings. The formulas that will be used mainly consist of the spring motion and the update formulas. When a stretched slinky is released from rest, instead of falling all at once like a rigid object, the slinky's bottom ends up staying suspended for a moment, even after the top begins to fall. This happens because the tension in the slinky must first relax and then travel downward before the lower coil begins to accelerate. In this lab, I modeled the motion of a stretched slinky drop from static equilibrium using both computational tools and experimental video analysis. Part 1 Tracker. The system is the spring, and the surroundings is everything outside the system, like gravity. I set the calibration length to 1 meter and plotted the mass at different frames. The tracker output the positions in the X and Y direction when it referenced from this video shown in the GIF. Part 2 Glow script. For the coding section, I referenced past code that mainly used gravity and the force of gravity and the force of spring, and I used that to create the coding for this specific analysis. I had to update the position and the velocity. I made the position initial position to be 0.421 in the x direction and 0.527 in the y direction, but I also had to use the spring formula to calculate spring force, and the glow script output this graph shown on the bottom, and on the right of that is the motion of the slinky. It doesn't show right now, it froze, but it was supposed to go horizontal and then drop to the negative y direction, similar to how the graph looks like. Part 3 Comparing models. For the behavior of the slinky, the experimental data or tracker showed that the bottom of the slinky remains still briefly while the top collapses, and similar to this, the computational model for the bottom also remains still until the relaxation wave hits it. The timing of the collapse, there's a slight difference between the two, with experimental data showing a slight variability due to real tension and other imperfections. And for the computational model, the timing depends strictly on defined spring constants and step size. For air resistance in tracker, it was present and it may have caused tiny effects, but for the computational model and glow script, it's typically ignored. Both also use the same position and velocity update formulas from Newton's second law. Part 4 Errors. Some possible sources of error include inaccurate calibration or scaling in tracker, and human error in making the position of the mass frame by frame. Part 5 The questions. For the first one, what does it mean? Why did it look like it was floating? Well, the slinky appears to float because the bottom of the slinky stays in static equilibrium for a short period. Even after the top is released, this happened due to the balance of spring tension and gravity. Before the slinky is dropped, the bottom is held up by the tension created from stretching the slinky. When the man released the top, the tension didn't disappear instantly, and it must have traveled down the slinky as a wave until this wave reached the bottom. The bottom still feels the same upward tension as before, which exactly cancels out gravity. As a result, the bottom does not move, and it looks like it's floating in midair. For the second question, what if the slinky had a larger radius? Would it have made a difference? If the slinky had a larger radius, the motion would still show the same floating effect, but the timing of the motion would change. A larger radius usually means that the coils are wider and slightly softer, which affect how the slinky stretches under its own weight. A larger radius slinky would stretch more in equilibrium. It would have a lower spring stiffness, or K. The tension wave that traveled down the slinky after it was released would move more slowly, and because of that, the bottom would appear to float or have a slightly longer duration. In this lab, I modeled and analyzed the motion of a falling slinky. By comparing my simulation to real video data, I confirmed that the bottom appears to float because it stays in tension equilibrium until the release wave reaches it. While my simulation reproduces this motion well, small timing differences appear due to assumptions about spring constants, air resistance, and slinky stiffness. Overall, my results confirm that the slinky's motion is fully consistent with Newton's laws. Thank you.